September 5th, 1944, 3:47 p.m. Cherbourg Harbor, France. Lieutenant John Bridge stands in ankle-deep water, staring at something that shouldn't exist. A spherical steel casing, roughly 3 feet in diameter, covered in what appears to be pressure sensors. Every sensor connected to detonators. Every detonator linked to 1,400 pounds of high-grade explosives. His commanding officer had given him 45 minutes, not because that was enough time, because in 45 minutes the tide would rise another 6 feet, submerging the device completely, making defusal impossible, and ensuring that when this mine detonated, it would obliterate the entire harbor infrastructure that the Allies desperately needed to supply their advance into Germany. Bridge had defused 17 naval mines during his career, standard German Teller mines, predictable, mechanical, logical. This was something else entirely. The German engineers called it the Teufelsei, the devil's egg. Intelligence reports suggested it was theoretically impossible to defuse. Every sensor covering its surface acted as both a trigger and a trap. Touch one, and you might trigger 3 others. Cut one wire, and a secondary circuit would complete. The British had never seen one intact. Every previous encounter had ended in detonation. Bridge had 45 minutes to figure out what the best German engineers had spent 2 years perfecting. This is the story of how a handful of British combat engineers solved an impossible puzzle while standing in rising water, surrounded by a weapon specifically designed to kill anyone who tried to stop it.
To understand why this single mine mattered so much, we need to grasp the logistical crisis facing the Allied forces in September 1944. The D-Day invasion had succeeded beyond expectations. American, British, and Canadian forces had broken out of Normandy and were racing across France. Paris had been liberated on August 25th. The German army was in retreat. Victory seemed within reach. But there was a catastrophic problem: supplies. Every gallon of fuel, every artillery shell, every can of food for the Allied armies still came through the artificial mulberry harbors on the Normandy beaches, over 200 miles behind the advancing front lines. The temporary harbors were breaking down under constant use. Storms had damaged critical sections. The supply chain was stretching to its breaking point. The Allied command needed a deep-water port, urgently. Cherbourg was the answer. Captured on June 26th, this French harbor had the capacity to handle 20,000 tons of supplies daily, enough to keep the entire Allied advance moving, enough to potentially end the war before Christmas. But there was a catastrophic problem. The harbor wasn't just damaged, it was systematically destroyed. German engineers under General Major Robert Sattler had spent weeks implementing Demolition Plan Cherbourg, a comprehensive strategy to render the port useless for months. They'd sunk ships in the main channels, demolished the lock gates, destroyed the cranes and unloading equipment, booby-trapped the remaining infrastructure, and throughout the harbor they'd placed specialized naval mines unlike anything the Allies had encountered. Standard mine clearance would take months. The Allied advance couldn't wait months. The American Logistics Corps estimated they had perhaps 3 weeks before the entire offensive ground to a halt due to lack of supplies. British Royal Engineers were tasked with clearing the harbor, fast. By early September, they'd made remarkable progress. Salvage crews had refloated several blocking ships. Engineers had jury-rigged temporary unloading facilities. Mine clearance teams had located and neutralized dozens of conventional explosives. Then, on September 5th, a diving team discovered something in the main berthing area That changed everything. The devil's egg.
The mine that Lieutenant Bridge was now staring at represented the cutting edge of German defensive technology. Traditional naval mines were relatively simple devices, a floating or anchored explosive charge with a contact detonator. A ship strikes the protruding horns, completing an electrical circuit, triggering the explosion. Dangerous, yes, but predictable. Bomb disposal experts could identify the trigger mechanism, isolate the power source, and render the weapon safe. The Germans knew this. They'd been losing mines to Allied disposal experts throughout the war. British and American engineers were getting too good at their jobs. So German military engineers developed a new generation of weapons, mines that fought back. The Teufelsee was the pinnacle of this innovation. Intelligence reports, gathered from captured German engineers and fragments of destroyed devices, suggested several terrifying features. First, multiple redundant trigger systems. The sphere wasn't covered in sensors for redundancy. Each sensor was an independent trigger. The mine could be detonated by pressure, magnetic field disruption, acoustic vibration, or simply removing it from water pressure. Cut one circuit, and others would remain active. Second, anti-tampering mechanisms. The device incorporated counter-surveillance features. It could detect the presence of metal detectors. It could sense changes in electrical fields caused by investigation equipment. Some reports suggested it even incorporated a timer that would detonate the mine if it wasn't triggered within a certain period. Third, cascade detonation architecture. This was the most diabolical feature. The sensors weren't just connected to the main explosive charge, they were connected to each other in a network. Triggering one sensor could activate others. The mine learned from tampering attempts. It adapted. British intelligence had collected reports of these weapons from captured documents and interrogated prisoners. The theoretical specifications were terrifying, but until September 5, 1944, no Allied engineer had seen an intact devil's egg. Now one sat in Cherbourg harbor, in the exact location where supply ships would need to dock, in shallow enough water that divers had discovered it, but in deep enough water that conventional disposal methods wouldn't work. You couldn't destroy it in place. The explosion would devastate the harbor infrastructure. You couldn't move it. Any motion sensors would likely trigger detonation. You couldn't ignore it. Every supply ship using the harbor would be at risk. The only option was defusal, the option the weapon was specifically engineered to prevent.
Lieutenant John Bridge wasn't supposed to be the one dealing with this problem. The senior bomb disposal officer for the Cherbourg sector was Captain Edmund Hunt, a veteran with 3 years of explosive ordnance experience. Hunt had personally cleared over 40 complex German booby traps and mine installations. But Hunt was 8 miles away, dealing with a collapsed ammunition bunker. Radio communication confirmed he couldn't return for at least 4 hours. The mine had been discovered at 3:15 p.m. The tide chart showed high tide at 4:30 p.m. At high tide, the mine would be under 12 feet of water. Diving bells and underwater defusal were possible in theory, but not with this device, not with sensors that might detect pressure changes from diving equipment, not with the complexity of circuits that needed visual inspection. If the mine couldn't be defused before high tide, the harbor would remain unusable until the next favorable low tide period, 2 days away. 2 days the logistics situation couldn't afford. Bridge was 26 years old. He'd completed Royal Engineers explosive ordnance training in 1943. He'd defused standard mines. He'd cleared German beach obstacles during the Normandy invasion. He was competent, experienced, but he'd never seen anything like this. At 3:50 p.m., he made the decision that probably saved his life.
He would assume nothing. Standard bomb disposal doctrine emphasized identifying the primary trigger mechanism and neutralizing it. Pattern recognition, experience, apply known solutions to known problems. But this wasn't a known problem. This was a weapon designed to kill people who relied on experience and pattern recognition. Bridge needed a different approach. He assembled a team of 3 other engineers: Sergeant William Hutchins, an electrical specialist; Corporal David Matthews, who'd worked as an industrial electrician before the war; and Private Robert Shaw, whose peacetime job had been repairing precision instruments. Bridge's instructions were simple. We're not trying to defuse this, we're trying to understand it. We have 40 minutes to figure out how it thinks.
At 3:55 p.m., with the water now halfway up the mine's spherical casing, Bridge's team began their investigation. Standard procedure would be using electronic detection equipment to map the internal circuits, but Bridge suspected the mine would detect such investigation. Instead, they started with pure observation. Hutchins noticed something crucial. The pressure sensors weren't evenly distributed across the sphere. They clustered more densely on the upper hemisphere. Why would German engineers do that? Matthews provided the answer. Because ships approach from above. They're prioritizing the kill zone. This revealed something important. The mine wasn't just designed to explode. It was designed to maximize damage to ships. That meant the engineers had prioritized certain trigger vectors over others. Bridge had his first clue. The weapon had priorities. It wasn't a perfect sphere of equal danger. It had an optimal trigger pattern. At 4:02 p.m., Shaw made the second critical observation. Between the visible sensors, he could see faint seams in the metal casing, regular intervals, too regular to be manufacturing imperfections. It's modular, Shaw said. The sphere is constructed from separate panels. This was revolutionary insight. The mine wasn't built as a single unit. It was assembled from components. That meant there had to be access points, places where German engineers could install and maintain the internal mechanisms. If the mine had access points, it had vulnerabilities. But where and how were they secured? At 4:08 p.m., with water now lapping at their thighs, Corporal Matthews spotted the answer. In the lower hemisphere, nearly invisible against the dark metal, were 4 small bolt heads, specialized bolts, requiring a unique tool, but definitely bolts. This created a paradox. If the mine was designed to prevent tampering, why have removable access panels? Bridge understood. Because German engineers needed it to service it. They built in a safe way to access the internals. We just need to figure out what makes it safe. The real question wasn't how to defuse the mine. It was how German engineers could work on it without killing themselves.
At 4:12 p.m., Lieutenant Bridge made a decision that violated every principle of bomb disposal he'd been taught. He was going to open the mine. Standard doctrine was clear. Never introduce new stresses to an unknown explosive device. Never create new pathways for triggers. Never assume you understand the internal mechanisms. But Bridge's logic was unassailable. German engineers had opened this mine. They'd installed the explosives. They'd connected the sensors. They'd sealed it. They'd done all of this without detonating it. There was a safe way to access the internals. The German engineers knew it. Bridge just needed to figure out what they knew. Hutchins fabricated a tool from a broken wrench and a piece of steel pipe. It approximately matched the bolt head dimensions. At 4:16 p.m., Bridge placed the improvised tool on the first bolt.
Everyone took cover behind a concrete piling 50 feet away. Everyone except Bridge. "If I'm wrong," he told his team, "you'll need to report what doesn't work." He turned the bolt counterclockwise, 1/4 turn. Nothing happened. Another 1/4 turn. Still nothing. The bolt loosened. Bridge removed it completely. The mine didn't explode. By 4:22 p.m., all 4 access bolts were removed. The water was now chest deep on Bridge, who stood at just under 6 feet tall. He had maybe 8 minutes before the mine would be completely submerged. He carefully lifted the lower access panel. Inside was a revelation. The internal structure wasn't a chaotic web of wires and sensors. It was organized, logical, color-coded. The German engineers had built this weapon to be maintainable. Every connection was labeled. Every circuit had a clear purpose. And there, in the center of the access cavity, was a simple mechanical switch, painted bright red, labeled in German, Sicherungsschalter, safety switch. This was how German engineers could work on the mine without killing themselves. They'd flip the safety switch, disabling the trigger mechanisms. They'd perform maintenance. They'd reset the switch. The mine would be armed again. But there was a problem. The switch had 2 positions. Currently, it was in what Bridge assumed was the armed position. But which direction was safe? Up or down? The label didn't specify. And if he guessed wrong, 1,400 pounds of high explosives would detonate instantly.
At 4:27 p.m., with water now reaching his shoulders, Lieutenant Bridge faced the simplest and most terrifying choice of his career. Flip the switch up or flip it down. He had no technical basis for the decision. No training, no precedent, just logic and intuition. Hutchins shouted from behind the piling, "German industrial standards. Safety positions are typically downward, gravity-assisted." It was a reasonable theory, but was it correct? Did naval mine engineers follow industrial conventions? Or did military specifications override civilian standards? Bridge thought about the German engineers who'd built this weapon. What would make sense to them? Then he remembered something from his basic training. British military switches typically defaulted to safe in the downward position. If a switch mechanism broke, gravity would pull it to the safe state. It was a fundamental safety principle. Would German engineers think the same way? At 4:28 p.m., Bridge made his decision. He would flip the switch downward. He called out to his team, "If this goes wrong, tell my wife I was trying to be clever." He placed his hand on the switch. The water was now touching his chin. In 60 seconds, the mine would be completely submerged. This was the last possible moment. Bridge flipped the switch down. For 3 seconds, nothing happened. Then, throughout the mine's surface, dozens of small indicator lights flickered on. Dim red LEDs, barely visible even in the late afternoon light. The mine was showing its status. The sensors were active, but disengaged from the detonators. Bridge had guessed correctly. At 4:30 p.m., with the tide now covering the mine's upper surface, Bridge and his team used wire cutters to systematically disconnect every sensor from its power source. With the safety engaged, they could work methodically. By 4:52 p.m., the mine was completely inert. A weapon that had taken German engineers 2 years to perfect had been defeated in 45 minutes by a lieutenant who understood one crucial principle. Even the most complex weapons need maintenance access, and maintenance access is always a vulnerability.
The successful defusal of the devil's egg had immediate strategic consequences,
With the main berthing area confirmed safe, Cherbourg Harbor became fully operational on September 12, 1944. Within 2 weeks, the port was handling 15,000 tons of supplies daily. The logistics crisis that threatened to halt the Allied advance never materialized. But the discovery had even greater long-term impact. The intact mine was immediately transported to British military intelligence facilities. Engineers spent weeks disassembling and analyzing every component. What they found revolutionized Allied understanding of German defensive technology. The devil's egg wasn't just an isolated innovation. Documents discovered inside the device revealed it was part of a larger series. The Germans had developed at least 17 variants, each optimized for different environments. Deep water mines, harbor defense systems, even land-based versions for infrastructure protection. More importantly, the analysis revealed the fundamental flaw in German mine design philosophy. By making the weapons too complex, too sophisticated, the engineers had created maintenance requirements, and maintenance requirements meant access points, and access points meant vulnerabilities. This insight transformed Allied bomb disposal doctrine. Instead of trying to understand trigger mechanisms, disposal experts began looking for maintenance access. The approach proved remarkably effective. Throughout late 1944 and early 1945, dozens of German advanced mines were neutralized using Bridge's methodology. Lieutenant John Bridge received the George Medal for his actions at Cherbourg. He survived the war and returned to civilian life as an electrical engineer. In a 1978 interview with the Imperial War Museum, he reflected on that afternoon in September. People think bomb disposal is about bravery. It's not. It's about understanding that someone built the weapon. Someone had to install the explosives, connect the wires, test the mechanisms. And whoever did that needed to do it safely. Every weapon has a way to be built safely. That's the same way to take it apart safely. You just have to think like the engineer who made it. The principles Bridge discovered remain relevant today. Modern explosive ordnance disposal teams still prioritize understanding how a device was constructed before attempting to neutralize it. The question isn't, how do we destroy this, but rather, how did someone build this without killing themselves?
The story of the devil's egg reminds us that the most sophisticated weapons are often defeated by the simplest insights. German engineers spent years developing a mine that seemed impossible to defuse. They incorporated multiple redundant triggers, anti-tampering mechanisms, and adaptive circuits. They created something genuinely innovative and terrifying. But they overlooked one unavoidable truth. They had to build it. And anything that can be built can be understood. This principle extends far beyond wartime engineering. Every complex system, whether it's a weapon, a security protocol, or a piece of software, requires maintenance. And maintenance access is always a potential vulnerability. The more complex a system becomes, the more maintenance it requires. The more maintenance it requires, the more access points it needs. Security through complexity is an illusion. True security comes from eliminating unnecessary complexity and rigorously protecting the essential access points that remain. Lieutenant Bridge survived the war because he understood this. He didn't try to be more sophisticated than the weapon. He looked for the human element, the point where German engineers needed to interact with their creation safely. And in that human element, he found the solution. If you found this story fascinating, you'll want to hear about the American radio operator who built a working transmitter inside a Japanese POW camp using nothing but spare wire and a damaged razor blade. That's coming in the next video. Hit subscribe so you don't miss it. And if you enjoyed learning about this incredible piece of problem-solving under pressure, leave a comment telling me which aspect of military engineering you'd like to explore next.
Remember, history's greatest victories weren't always won on battlefields. Sometimes they were won in harbors, by engineers standing in rising water, refusing to assume the problem was impossible.